Hello, today we're going to do some sample problems here for modes of vibration. We're going to assume for air the speed of sound to be 340 meters per second in this particular situation. So here we go with number one. We're going to find the fundamental frequency of an open pipe. So the key thing is know what kind of pipe we're dealing with. An open pipe that is 1.7 meters long. One of the key things in doing these is to draw the picture. So it's an open pipe. I'm going to draw it open at both ends. And it's fundamental. So the fundamental, the waveform looks like this. It's got antinodes at both ends. And we know that in this case, for the fundamental, the length is lambda 1 over 2. The length of the pipe is half the wavelength. And if we know that that length of the pipe is 1.7 meters long, then we know, multiplying both sides by 2, we get the wavelength to be 3.4 meters. Excuse me. Now, what we want to find is the frequency. The frequency, using the wave equation, that's V equals F lambda, the frequency would be V divided by lambda. So that would be 340 meters per second divided by 3.4 meters. The meters will cancel. You'll end up with reciprocal seconds, which is hertz, and we will get 100 hertz. In our next problem, we're going to find the frequency of the second harmonic of an open pipe. Unlike the first harmonic, second harmonic, once again, draw the picture. It's open pipe, same length pipe, but now what we have is we have the second harmonic. That looks like this. And for the second harmonic, for an open pipe, the length of the pipe is simply equal to the wavelength. And therefore, we know that the wavelength is 1.7 meters. And to find the frequency would be V over lambda, and that would be 340 meters per second divided by 1.7 meters, and we get 200 hertz. Of course, the second harmonic will have twice the frequency of the fundamental for the same pipe. In the third problem, we find the fundamental frequency of a closed pipe of 1.7 meters long. So now this is a closed pipe, so I'm going to draw this a little bit different. And when we do the fundamental for a closed pipe, it looks like such. And the equation for that is the length of the pipe is a quarter of the wavelength for the fundamental, or also known as the first harmonic. And if we know this to be 1.7 meters in length, 4 times 1.7 would be the wavelength. So the wavelength would be 6.8 meters. To find the frequency, we would take 340 meters per second, divide that by 6.8 meters, and you would get 50 hertz. In number 4, we're going to find the frequency of the fifth harmonic of a closed pipe. Okay, so we have a closed pipe, still the same length pipe. It's open at one end, closed at the other. And the fifth harmonic looks like this. Each segment, each full segment is half a wavelength. So this is a half, a second half, and then half of a half, which is a quarter. So we know that the length will be, which is 1.7 meters, is equal to 5 lambda 5 over 4, fifth harmonic. So to find the wavelength of that fifth harmonic, we're going to multiply both sides by 4, and we're going to divide by 5. And when you do that calculation, you're going to get a wavelength of 1.36 meters. Of course, to find the frequency, it is, once again, 340 meters per second divided by 1.36 meters. The meters cancel. You end up with reciprocal seconds, which is hertz. And that comes out to be 250 hertz. Number 5, we find the wavelength of the third harmonic in a 65 centimeter long string. So this is now a string, the third harmonic. How do we draw the third harmonic? It looks like this. And we should know that the length of the third harmonic, in this case, which is 65 centimeters, would be 3 lambda 3 over 2. So that's the third harmonic. Each segment is a half a wavelength, so that's 3 halves. When you solve for the wavelength, you will multiply both sides by 2 and divide both sides by 3, and you will get 43.3 centimeters, or we might want to write that as 0.433 meters. Either way is fine. Now, problem number 6, we're going to start working some of these problems backwards. So what we have is we start with a frequency of 320 hertz. Using the wave equations, solving for lambda, lambda would be V divided by F, or 340 meters per second divided by 320 hertz. Remember, hertz is reciprocal seconds, so it cancels out the reciprocal seconds in the numerator. You're left with meters, and we get a wavelength of 1.0625 meters. But we want to know how long we have to cut this pipe to get this frequency. So if you're making a musical instrument, how do we do this here? Well, this is a closed pipe. That means it's closed at one end, it's open at the other, and we're dealing with the fundamental. So with the fundamental, it looks like this. And we know that the length of this pipe is simply a quarter of the wavelength. And we know the wavelength. It's 1.0625 meters. Divide that by 4, and we need to cut a pipe that is 0.266, or almost 27 centimeters. Number 7, find the length of an open pipe with a fundamental frequency of 320. So once again, we have a frequency of 320 hertz. Same as the previous problem, so we know that the wavelength is 1.0625 meters. This is a fundamental of an open pipe, so we draw the open pipe, and the fundamental of that looks like this, and we know that the length of this pipe is lambda over 2. And so if we know the wavelength is 1.0625 meters, and we simply divide that by 2, we get a pipe that's twice as long as its closed pipe with the same frequency. Number 8, we want to find the length of a closed pipe with a fifth harmonic frequency of 512 hertz. Well, we know the frequency, 512 hertz. And we know the velocity, so we can find the wavelength. That's of the fifth harmonic. So we know it's 340 meters per second divided by 512 hertz. and that's going to be 0.664 meters. That's how long the wavelength is. But how long do I have to make this pipe? The key is to draw the picture. It is a closed pipe. Open at one end, closed at the other. And the fifth harmonic looks like this. Okay, so we have to realize each segment is half a wavelength. So this is 1/2, a second half, and half of a half. So in essence, what we have is the length of this pipe is 5/4. This is 2/4, 3/4, and a 1/5 of the wavelength. So we take 5 times 0.664 meters over 4, and we will get 0.83 meters. That's how long you'd have to cut that pipe in order for it to resonate at 512 hertz when the speed of sound in air is 340 meters per second. And we'll do one more, number 9. A certain guitar string has a length of 90 centimeters and a fundamental frequency of 540 hertz. We're going to find the speed of the wave in the string. So we know that the frequency is 540 hertz, and we know that the speed of the wave in the string is going to be the frequency times the wavelength. Well, we know the frequency, so we've got to find the wavelength. Well, this is a string, and we're talking about the fundamental. So the fundamental looks like this. That's just one segment. And we know that when we have just one segment, the length of the string is each segment is half of a wavelength. And that's equal to 90 centimeters. Well, if half of a wavelength is 90 centimeters, the whole wavelength must be 180. Multiply both sides by 2. That would be 1.8 meters. And now we're going to find the speed of the wave. We're going to take the frequency, 540 hertz, and we're going to multiply it by 1.8 meters. And we're going to get 972 meters per second. That's the speed of the wave in the string. That's not the speed of the wave in the air. Okay, so I hope this helps you with all the problems.